Hi, my name is Eduardo Noriega, and today I'll be presenting our final project for the Design of Control System course. On this project, we focus on modeling, designing, and validating control systems for a DC motor, later used on a differential robot. Now let's explore each part in more detail. The system consisted of a motor, a CHF GM3865520 DC motor, with a permanent magnet, integrated gearbox, and a quadrature encoder for the speed feedback. Later, we use an Arduino for its simplicity to generate the PWM signals that adjust the speed and direction, fed into an IVT2 H-bridge powered by a 12-volt DC supply. This encoder data was used to identify the motor transfer function. With data, identify motor model using the least squares method, LSM, to derive the transfer function from the data, the PWM input to the angular velocity output. We validated was done, comparing the experimental step response with simulations. Despite minor variations due to encoder noise, key dynamic property, rise times, overshoot, and settle time, it really matched closely what was expected, both confirming the model's accuracy for control design. After that, we designed a PID controller for speed relation using the proportional, integral, and derivative actions, the PID, to dynamically adjust motor speed. At the start, MATLAB was used for the initial tuning, resulting in gains of 0.53 for the P, 0.194 in the I, and 0.019 for the D. In this and a continuous model. These were further refined for the discrete systems in the real motor to ensure stability. Now, for the real motor, to validate the PID controller, we applied set points of 100, 150, and 200 RPM. The motor tracked these set points effectively with minimal error with the new tuning and with a feasibility of the controller operating within the PWM limits. Also, the system maintained a steady state of error like 5%, 7 RPMs more or less. And the speed response showed no oscillations at all, ensuring robust control even during set point changes, which was pretty good. After that, we extended that PID control to the differential robot with two independently controlled wheels that also used that PID before design. And the robot movement was guided with a PID control for each wheels, minimizing distance and orientation error with two constant control variables, which were KP distance that adjusted the speed toward the target and KP orientation that corrects angular alignment to the target. The KP distance was way shorter than the KP orientation since the distance was so it was no aggressive that movement, and the KP orientation was to be more effective to going through the target. So at the end, it started a bit oscillating, finding the way, and then going in a straight line. So the trajectory control system was validated through these simulations since the robot reached the target accurately in the better approach since there's no obstacles in the space. It's operating smoothly way in mechanical constraints, and the trajectory closely followed the SR path with minimal deviation, to be honest. At the end, in summary, we successfully modeled and controlled a DC motor using a PID controller and extended that approach to a differential robot for a trajectory tracking. Both experiments and simulations align closely what we expected, validating our design implementation. So that was all. Thank you for watching.